Welcome to this complete guide on the periodic table for GCSE Chemistry. We'll cover everything from its structure and trends to key groups and exam technique. Today, we will be covering four main topics: the structure of the periodic table, key groups like alkali metals and halogens, trends and reactivity, and finally, the history and electronic structure behind the table's layout. The periodic table is a systematic arrangement of all known chemical elements. It organizes elements so that patterns in their properties become clear, making it a powerful tool in chemistry. Elements are arranged in order of increasing atomic number, which is the number of protons in the nucleus of an atom. Each element has a unique atomic number. The table is organized into periods, which are horizontal rows, and groups, which are vertical columns. There are 7 periods, and elements in the same group share similar chemical properties. Elements in the same group have similar properties because they have the same number of outer electrons. This leads to similar reactions and gradual trends in properties down the group. The periodic table is roughly divided into metals on the left and non-metals on the right. A diagonal staircase line separates the two. Metals are typically shiny, solid, good conductors, malleable, ductile, and have high melting points. Non-metals are dull, have varied states, are poor conductors, and are brittle when solid with low melting points. Now we will focus on Group 1, the alkali metals. They are reactive, soft, and always keen to lose an electron. Group 1 includes lithium, sodium, potassium, rubidium, cesium, and francium. They are soft, low-density metals with one electron in their outer shell. Alkali metals react vigorously with water to produce hydrogen gas and a metal hydroxide solution, which is alkaline. Reactivity increases as you go down. Group 1. Lithium reacts steadily, sodium more vigorously, and potassium very vigorously, burning with a lilac flame. Reactivity increases because atoms get larger down the group. Inner electron shell shield the outer electron, decreasing nuclear attraction. The outer electron is lost more easily in a reaction. Our next key group is Group 7, the halogens. These are colorful, reactive nonmetals that love to gain an electron. Group 7 contains fluorine, chlorine, bromine, iodine, and astatine. They are all nonmetals with 7 electrons in their outer shell, just one short of a full shell. Chlorine is a yellow-green gas used for disinfection. Bromine is a red-brown liquid that produces a choking orange vapor. Iodine is a dark gray solid that sublimes to a purple vapor when heated. Reactivity decreases as you go down. Group 7. Halogens react by gaining one electron to complete their outer shell. As the atom gets larger going down the group, the outer shell is further from the nucleus, and inner shells provide greater shielding. This makes it harder to attract an extra electron, decreasing reactivity. A more reactive halogen can displace a less reactive one from a solution of its salt. For example, when chlorine is added to potassium bromide, displacement occurs, and the solution turns orange-brown as bromine is produced. This table shows the results of displacement reactions. Color changes confirm displacement, while no change means the added halogen is less reactive than the one already in solution. We now move to Group 0, noble gases. They are irresistible, unreactive elements, perfectly content on their own. Group 0 includes helium, neon, argon, krypton, xenon, and radon. They are all colorless gases at room temperature with full outer shells, making them extremely stable. Noble gases are unreactive because they have a full outer electron shell. Since atoms react to achieve a stable configuration, noble gases, already having one, have no reason to react. The boiling point increases as you go down. Group 0. As atoms get larger, the intermolecular forces between them get stronger. More energy is needed to overcome these forces. Noble gases have important uses. Argon is used in light bulbs to prevent the filament from burning away. Neon is used in signs because it glows bright red-orange when electricity passes through it. Helium is ideal for balloons and airships because it is less dense than air and non-flammable. The next section covers transition metals, strong, versatile elements at the heart of everyday materials. Transition metals occupy the central block of the periodic table between groups 2 and 3. They include familiar elements like iron, copper, zinc, nickel, and titanium. Transition metals are excellent conductors of heat and electricity and have high density and strength. They form colored compounds and are useful catalysts in industrial processes. Transition metals contrast sharply with alkali metals in properties like density, melting point, reactivity, hardness, and the compounds they form. This table summarizes these key differences. The story of the periodic table begins with Dmitri Mendeleev. He arranged elements by atomic mass and property, bravely leaving gaps for undiscovered elements. Mendeleev published his table in 1869. His predictions for gallium and germanium were later confirmed. In 1913, Henry Moseley refined the table by ordering elements by atomic number, resolving anomalies, and establishing the modern table. Mendeleev used atomic mass, which resulted in anomalies. Moseley's use of atomic number, based on the number of protons, fixed these issues and ensured that all elements were placed in the correct chemical groups. Next, we will cover electronic structure, which is the key to understanding why the periodic table looks the way it does. It's not just organization, it reflects atomic reality. The electronic structure, or configuration, explains the periodic table's layout. Elements are grouped by shared physical properties, which directly depend on the arrangement of electrons in shells. The period number an element belongs to indicates the number of electron shells its atoms have. For instance, sodium in period 3 has 3 electron shells with the structure 2, 8, 1. For groups 1 through 7, the group number corresponds to the number of electrons in the outer shell. Group 1 elements have 1 outer electron, Group 6 has 6, and Group 0, noble gases, have a full outer shell. Knowing the electronic structure allows you to predict an element's position and chemical behavior. Count the shells for the period number and count the outer electrons for the group number. Finally, we focus on exam preparation, covering trends, definitions, and common questions you will encounter. Make sure you know these key definitions: atomic number, period, group, electronic structure, displacement reaction, and noble gas. These form the foundation of your knowledge. Review the trends for groups 1, 7, and 0. Group 1 reactivity increases down the group, while Group 7 reactivity decreases. Boiling points increase down both Group 7 and Group 0. You should be able to predict trends, displacement reactions, electronic structure, and compare properties between metals and non-metals in exam questions. For extended writing questions, use a structured approach. State the trend, give the reason related to electron shells, link to the mechanism of attraction/shielding, and conclude on the reactivity change. Before your exam, check this list. Ensure you understand the table structure, group trends, electronic structure links, and the history of the table's development. The periodic table is elegant and fundamental to chemistry. Good luck with your revision. Refer back to this video whenever you need a quick recap, and remember, every trend has a root in atomic structure.